Hello, today we're going to be covering static electricity and charge, and we're going to be focusing ultimately on conservation of charge, but we're going to build up to that. First, let's take a look at the founding father of electric charge. Now, you might recognize the guy in the picture with the kite as being Benjamin Franklin. When Benjamin Franklin demonstrated that lighting was related to static electricity, he made a connection that is now part of the evidence that all directly experienced forces, except the gravitational force, are manifestations of electromagnetic force. He was a physicist who first thought of electric charges in terms of positive and negative, even before they knew what an atom looked like. Elements of charge. The figure shows a simple model of an atom with negative electrons orbiting its positive nucleus. The nucleus is positive due to the presence of positively charged protons. Nearly all charge in nature is due to electrons and protons. Negatively charged objects have an excess of electrons. Positively charged objects have a lack of electrons. E is used to represent the elemental constant, which is the charge of a proton. It's positive when it's a proton, or electron. It would be negative if it's an electron. The absolute value of E is 1.6 times 10 to the negative 19 coulombs. Again, if we're dealing with electrons, this would be a negative 1.6 times 10 to the negative 19 coulombs. Some of the most basic characteristics of static electricity include the effects of static electricity are explained by electric charge. There are only two types of charge, one called positive, the other called negative. Like charges repel, whereas unlike charges attract. So if you have a negative and a negative, they repel. If you have a positive and a positive, they repel. But if you have a negative and a positive, they attract. The force between charges decreases with distance. You'll see this more in the next video about Coulomb's law. Law of conservation of charge. Charge is constant in any process. So if you have two neutral objects and then both of them become charged somehow, they're going to have equal and opposite charges so that the total charge is still zero. If you have one negatively charged object and a neutral object and they interact, the total charge should still be negative. Q1 plus Q2 before the interaction is going to be equal to Q1 plus Q2 after the interaction. Now, this does not necessarily mean that Q1 and Q2 have the same values before and after, but their total is the same before and after. Hence, if a closed system is neutral, it will remain neutral. Similarly, if a closed system has a charge, say negative 10e, it will always have that charge. The only way to change the charge of a system is to transfer a charge outside, either by bringing in a charge or removing a charge. But if it's possible to transfer a charge outside, the system is no longer closed or isolated and is known as an open system. There are three main methods used to charge objects. We can charge by friction, charge by contact, and charge by induction. Let's take a look at those. Here we have a glass rod and a silk cloth. So a glass rod becomes positively charged when rubbed with silk, while the silk becomes negatively charged. The charge on both objects will be equal and opposite because of the conservation of charge. So as you can see, the glass rod is attracted to the silk because their charges are opposite. The silk is negatively charged because we just rubbed off some electrons from the rod onto the silk. Two similarly charged glass rods will repel. Two similarly charged silk cloths will also repel because they're both negative. So in these three cases, you will see that the opposites attract. The like charges repel. A positively charged rod is brought near the tip of an electroscope, attracting electrons at the top and leaving a net positive charge on the leaves. Like charges in the light flexible gold leaves repel, separating them. This is called electrostatic repulsion. The electrostatic repulsion in the leaves of the charged electroscope separates them. The electrostatic force has a horizontal component that results in the leaves moving apart, as well as a vertical component that is balanced by the gravitational force. Similarly, the electroscope can be negatively charged by contact with a negatively charged object. In this example, A, B, and C, we are charging it with a positively charged object. When the rod is touched against the ball, electrons are attracted and transferred, reducing the net charge on the glass rod, but leaving the electroscope positively charged. The excess charges are evenly distributed in the stem and leaves of the electroscope once the glass rod is removed. The leaves separate due to electrostatic repulsion once again. Now there's two cases for charging by induction. Here we're going to take the rod and two spheres. So two uncharged or neutral metal spheres are in contact with each other, but insulated from the rest of the world. So we're calling this a closed system. Entering this closed system, we have a positively charged glass rod, and it's brought near the sphere on the left, attracting negative charge and leaving the other sphere positively charged. This is called polarization. The spheres are separated before the rod is removed, thus separating the negative and positive charged. The spheres retain net charges after inducing rod is removed without ever have being touched by a charged object. So there is no contact here, and the net charge on both the spheres are going to be 0. One is negative and one is positive, but they will have equal and opposite charges. So now we're going to charge by induction using a ground connection. A positively charged rod is brought near a neutral metal sphere, polarizing it. The sphere is grounded, allowing electrons to be attracted from the Earth's ample supply. So this kind of counts as the second sphere. So the ground connection is broken. You'll notice that the rod is still there. And then the positive rod is removed, leaving the sphere with an induced negative charge. Once we introduced the ground, we kind of created an open system for a quick split second, and that allowed infinite negative charges to come in. Alright, lastly, we're going to have a little comparison between conductors and insulators. We'll see what's different and what's the same. So the main thing about conductors is that they allow charges to move about freely, as opposed to insulators who do not allow charges to move about freely. Conductors can be polarized, and what this looks like is that if I bring a charged object near the conductor, the charged object here being the gold rod, we'll see that the charges separate all throughout the conductor. Whereas with insulators, they can also be polarized, But when the charged object is brought near the insulator, the individual molecules are charged. And so it's just the orientation of each molecule kind of changes so that the positive charges are closer to the negative charge source. What we want to observe about this is that while both conductors and insulators can be polarized, you have more movement of charge with the conductors. Therefore, you may get a stronger attraction. We also want to note that unless it's in connection with the rod and electrons move in or out of the object, you will still have a net charge of 0 in both cases. Polarized just means you have separated the charges in an area. Well, that's it. For the next video, you'll probably be learning a little bit more about Coulomb's law and electric fields.